clear. I cannot say with 100% certainty that there is no God. I can say with 100% certainty that I wouldn't want to live in a universe with one.
Talking about philosophy. We've seen a lot of cosmology, but please connect this to the philosophy.
All right, so when I was asked to take part in this session, I first asked the organizers, why don't you ask a cosmologist, because he will have a very interesting cosmological discussion. And they said, no, there is all kinds of theology involved. And I said, well, why should I discuss theology with Professor Krauss from the Ecosphere? Well, I would call myself an atheist, and he calls himself an anti-theist, but I think the difference will not be very, very big indeed. And then in the end they said, well, we invited you because you can speak English. So,
that's not true.
Of course, I'm not a cosmologist. I have some interest in cosmology. When I spent my sabbaticals in Princeton, which I did in the 1990s, I used to follow cosmology courses, so I'm interested. And I have many questions, but you have to see the point of view from which I'm asking these questions. So what are philosophers doing? Philosophers are first of all interested in logic. What types of argument are valid arguments and what types of arguments are not valid arguments. Then they're interested in philosophy of science. For instance, what is the likelihood of a specific hypothesis? Of course, we have hypotheses that are very well confirmed. We have also hypotheses that are very speculative. And I'm interested, when I looked at scientific theories such as Darwinism, well, how certain is this theory? What is the evidence? How likely does the evidence make the theory, and so on? And all kinds of instruments we developed in order to assess that. And then, of course, we are interested in our general world picture. So the general world picture.
I'm waiting for me to fix it.
Yeah.
Okay. It has been fixed? You can hear me?
Yes.
Very good. So the last interest of a philosopher is the general world picture. How should we relate religion to science, for instance? Well, there are lots of views on this. Now, I have asked a few questions, but the ideas that we are going to discuss, although we agree among lots and lots of things. So my first question is concerned with the Kraussian hypothesis about the origin of the universe. Now, most of the stuff we heard this evening is quite standard physics and cosmology. But I think there is a specific hypothesis which is defended by Krauss, and which you might summarize very, very briefly by saying that of course, the universe originates from nothing, first from quantum mechanical processes plus inflation. So these two big parts of the theory he joins together. He supposes that when particles pop into existence and disappear again, that's a process we have studied quite well in quantum mechanics, but he extrapolates that to the universe as a whole and plugs in inflation, and then we get the origin of our universe, very, very briefly. Yeah. Now, of course, there are many other hypotheses about the Big Bang Theory and so on. So there is, for instance, the bouncing universe hypothesis, and there are all kinds of other hypotheses. So my first question would be, are these pure speculations of theoretical physicists, or can we form predictions on the basis of these speculations, which has been confirmed? How does your speculation, how is it related to the other possible scenarios of the origin of the universe? And is there any empirical way of deciding this, or we don't know it? Now, there is a quote in your book. I read the book.
Very good.
So there is a quote.
Although all that matters is buying it. You don't have to read it.
That's right. That's true for my book as well. Now, one thing you say on page Roman 13 is that Roman numbering. All signs suggest that this is how our universe could have arisen, and then you stress could, and you say, I stress the word could here because we will never have enough empirical information to resolve this question unambiguously. So it seems to be the case that you acknowledge that the theory is quite speculative and that we can't decide, well, empirically. There is another quote on page 72. Until we have a theory of quantum gravity, as it is called, we can't trust extrapolations that go beyond this limit. So I phoned one of my quantum gravity colleagues at the University of Utrecht. In fact, she moved to Nijmegen. And I said, well, this theory of Krauss, how speculative is it? What is the likelihood? And she says, well, this is very, very speculative. There are not So my first question is, well, how seriously should we take this hypothesis? Now, second question.
Shall we answer?
Well, no,
The
yes.
first question
We're chomping at the bit.
All right.
So you ask how reasonable is this compared to other ideas, and the answer is this one's right. But no, to be a little less facetious, there's nothing, the details are extremely speculative about how it may have happened, but there's nothing speculative about the processes. Namely, let me make it quite clear, there are other ideas about a bouncing universe, but no physicists take them seriously. They're really ugly. The only people who like them are the people who wrote them down, but they're so contrived, without any fundamental ideas associated with them, that it's an embarrassment that we talk about them publicly. But besides, look, the Big Bang happened unambiguously. Let's get to the things that we know. The Big Bang, we can extrapolate the history of the Big Bang back to a millionth of a second, and we get everything right. So all the interesting stuff that we don't know happened in the first millionth of a second. Okay? Now, the point is, how can we empirically test these ideas? Because you're right, without empirical tests, it's philosophy. And who cares? So what's really remarkable is we look for ways to test, and in fact, there's a way you can test for inflation, as opposed to bouncing universes, that doesn't depend upon just talk. Two things. One, you can calculate in inflation quantum fluctuations. You can actually do the calculation, and you can predict that one of the most amazing predictions of inflation, which is again unheralded, is that those quantum fluctuations at the very smallest scales get magnified and turn into everything we see. If it's really true, we are here due to quantum mechanics. All the lumps in that microwave background radiation are due to quantum mechanics. And we can predict the distribution of lumps, and we can predict, because quantum mechanics allows us to do that. And what do you get? You get exactly what we see. Now, does that prove inflation was right? No, because you've got to make a prediction that's falsifiable, so it's consistent. But one of the other neat predictions of inflation is that you not only produce lumps in matter, but you produce lumps in gravity. You produce what are called gravitational waves. And so one of the things we're looking at with the next generation of satellites is to look for gravitational waves. Because inflation makes certain predictions about gravitational waves coming from the early universe that would happen when this expansion happened. So it would be profoundly important. In fact, the Planck satellite, which is up there right now, is looking for gravitational waves. One of the interesting things is that this bouncing theory, besides being wrong, actually makes a very different prediction. And so you could distinguish between those ideas empirically. So there's a great deal of evidence that's consistent with inflation right now, but we haven't been able to prove it.
How many other hypotheses are in the market?
None. None from first principles. None. And I'm the first person to be skeptical of ideas. And inflation right now is the only idea from first principles that is consistent with everything we see. That doesn't mean it's right. And that's one of the reasons if I give a science lecture, which I could give at the university here, I talk about my skepticism about the tests of inflation. Most physicists nowadays would say inflation happened because we measured all this. And you should, and as a philosopher, of course, you would agree that that's inappropriate. Unless we can falsify the theory, a la Popper, then we shouldn't say in fact, we don't prove. One of the other big misunderstandings of science is we never prove things to be right. We only prove things to be wrong. That's all science can do. It can never prove anything to be right. Because
Professor Krauss, can I just, you seem to like to talk about your theory being right.
It's not my theory.
It's the theory, okay? You use the word right and wrong quite a lot, so...
What I should do, whenever I use the word right, what you should interpret to me is not wrong. There's a huge difference.
Okay.
There's a huge difference. What's wrong? So let me get to the sentence I was going to say. Science can prove things wrong. It can prove things wrong by making a prediction that disagrees with the experiment. If you make a prediction and it disagrees with the experiment, you throw the theory out. That's what's great about science. No matter how elegant or beautiful or desirable the theory looks to you, you throw it out like yesterday's newspaper. And all you do is keep doing that with the wrong theories. And the theories that you haven't yet been proved wrong, we think have more likelihood of being right. So this theory, these ideas are, first of all, the notion of inflation is very well founded. But the notion of quantum gravity creating spontaneous universes is that if gravity is a quantum mechanical theory, and we don't know the theory, because space and time become quantum mechanical variables, and because quantum mechanics requires fluctuations, it is a required part of the theory that spaces will be created from nothing. We don't know how, but any theory of quantum gravity will allow for that possibility. So that's also not speculative, even though we don't have a theory. Now, it could be, and I'll admit this, it could be that at some fundamental scale, gravity is inconsistent with quantum mechanics. In fact, Gerard de Tuft, who's here in Holland, and has a good track record, thinks that maybe quantum mechanics is wrong at some scale. I think he's wrong. He's probably the only one who's arguing for that, but we don't know the answer yet. So, you know, the point is, it's plausible. All I argue is that everything, extrapolating what we know now, makes it completely plausible. And it could have been different. It could have been that the universe isn't flat. It could have been that it isn't dominated by dark energy. It could have been, lots of things could have been the case.
It could even have been created by God.
Well, it could have been, and let me point that out. I can't prove it wasn't.